Hello everyone, hope you are all doing fine. Welcome to the fourth lecture on electrostatics. In the previous lectures on electrostatics, we have learned about Coulomb's law. We have combined the concept of Coulomb's law to conduction concept, to equilibrium concept, to the concept of simple harmonic motion. In some competitive exams like JEE, NEET, they don't ask the questions just based on the formulas. Rather, sometimes they ask the questions to know your conceptual understanding, conceptual skills. Okay, in this video, we are going to combine the Coulomb's law, that means the electrostatic force between the charges, to the vertical circular motion. So yes, my name is Vijay, Krishna, and you are watching UpPhys channel. Let's get started. Let's define the question first. Okay, right. I have drawn the vertical circle here, okay, to make it look better. Now I am going to consider a particle of mass m which has a charge capital Q. A particle of mass m which has mass m and charge capital Q. Mass m and charge capital Q. It is held with the help of a string, it is held with the help of a string right here. Okay, what kind of string it is? Massless, inextensible and non-conducting string. Okay, I have taken a particle of mass m and charge q which is held freely with the help of a string which is massless, inextensible and non-conducting string of length L, let it be of length L. now what I am going to do is, this string I have fixed this string about this point, about point O, about point O. now let's repeat the given data again. I have taken a particle of mass m and charge capital Q which is held freely with the help of a string of length L which is massless, inextensible and non-conducting, which is fixed about point O. Now what I am going to do is, I am going to take another particle of charge small q, another particle of charge small q, another particle of charge small q I have taken. That particle I have placed exactly at the fixed point O. Okay, now let's analyze the given scenario. Now the question is, what is the minimum velocity which is given to the particle, at the bottom such that this particle makes the vertical circle. If you can clearly recall the vertical circular motion concept, the minimum velocity at the bottom is root phi gr, as you can remember, where r is the radius of the vertical circle, g is the acceleration due to gravity, and at this point it is root 3 gr, and at this point what is it? Root gr. Okay, now let's analyze the given scenario. Now what is the minimum velocity which is given to the particle at the bottom such that it clearly makes vertical circular motion. Okay, now what I am going to consider is, I am going to assume the velocity which is given to the particle at here is u. Now as it is making a vertical circular motion, let the particle's velocity at the topmost point is v, at the bottom it is u, at the top it is v. You can take velocity bottom, velocity top as well. Okay, right. Now let's analyze the given scenario. Okay, let's use the forces for that. Now first let us look at the bottom point. Look at the bottom point. Now, as the particle has mass, its weight is acting vertically downwards, which is mg. Weight is acting vertically downwards, which is mg. Now, another force, as it is moving in a circular path, it will have centrifugal force, or even you can take centripetal force also. When you consider the centripetal force, you have to consider that force as net force. When you use centrifugal force, it's a pseudo force, so you use that force to balance the forces. Okay, so as I am using centrifugal force here, which is acting away from the center, so I am considering the balancing forces rather than looking at the net force. Okay, right. So the centrifugal force, let it be, what is it? Centrifugal force is mu square by L, where L is the length of the string, which can be considered as radius r. Okay, mu square by L, because it has velocity u here. Now, so this is the centrifugal force and the weight of the object that I have already represented. And as there is string, there exists tension also. That tension is acting in this direction, T, acting in upward direction towards the center, which is T. Now if you look at these forces, we have left with one more force. There are two charges, one is capital Q, another one is small q, which are separated by a distance small l. From Coulomb's law, these two charges separated by distance l, then there exists force, that too repulsive force, as these two charges are of same nature, positive. So repulsive force, I am going to write the repulsive force here. Repulsive force is K small q capital Q by R square. Capital Q small q by R square. This is the electric force. Okay, I am going to write here, it is electric force, and this is centripetal force, and this is weight due to gravity. Okay, these are the forces acting on the particle at the bottom. And now let's go to the topmost point here. Okay, now the particle is here. Okay, now at this point also the weight of the particle acts vertically downwards. Mg is acting vertically downwards. In addition to that, there exists tension that is also along the string towards the center. Now, in addition to these two forces, as this charge is capital Q, okay, now there exists repulsive force again. The electric force would be same, F electric is equal to K small q capital Q by L square. Sorry, I have written this force as R square. So I am going to write the forces here, K small q capital Q by L square. Okay, right. Now K small q capital Q by L square. Electrostatic force between the two charges is not changing because the separation between the charges is not changing because they are connected with the string which is not breakable, which is inextensible, and the charges are not changing wherever it is going, wherever they are moving. So the electric force between the two charges remains the same. Now we have left with one more force, that is mv square by L, centrifugal force. So these are the four forces again acting on the particle at the topmost point of the vertical circle. Now even if you look at the intermediate point like this one, let's say the particle is somewhere here at some point, at some time, the tension acts in this direction, whereas electric force acts in this direction, and electric force acts in this direction, and centrifugal force acts also in this direction. Okay, whereas the weight of the object acts vertically downwards, mg. Okay, right. So all the three forces are acting along the same line, whereas the weight is acting perpendicular to all these forces. Okay, so as these forces are perpendicular to each other, the weight has no influence on these three forces. Okay, right. Now, okay, hope you have understood the analysis of the system that we have considered, or the scenario that we have taken. If you find difficulty in understanding it, please watch the video again so that you will be able to follow it. If you are still unable to follow, please comment below. Okay, right. Let's move ahead. Okay, now what I am going to do is I am going to take the condition which is given in the question. Okay, what is given in the question? What is the minimum velocity which is given to the particle at the bottom? So instead of giving any random velocity here, I am giving the minimum velocity so that it makes complete vertical circle. Complete vertical circle. So minimum velocity, I am taking the condition u is what? Minimum velocity. Minimum velocity. Minimum velocity at bottom. Minimum velocity at bottom, which is given to the particle such that it is still making the vertical circle. Okay, what happens if I give the minimum velocity at the bottom? It is making the vertical circle, still it is making the vertical circle, but according to the condition, what exactly happens is, by the time it reaches the topmost point, the string connecting the two points, the string just about to slack. That means the tension slowly decreases as it moves to the topmost point, slowly decreases, and the tension, that means the string just about to slack, in the sense the tension just about to zero, not exactly, may not be zero, just about to zero or nearly equal to zero. So if we take for this minimum velocity at the bottom condition, the tension at the topmost point, is equal to 0. Tension at topmost point is equal to 0. Okay, as tension at topmost point is 0, I can use this condition and substitute in this equation. Equation that I have not written yet, I am going to write it. Okay, so tension is to be taken 0 when we have given minimum velocity at the bottom. Hope this point is clear. Tension, we have taken it as 0 at the topmost point because the string just about to slack, as we have given minimum velocity at the bottom to make the vertical circle. Okay, now I am going to write the equations here by using balancing the forces. Okay, at the topmost point, at top, okay, at top, if I clearly write the equation, there are two forces above the particle and two forces below the particle. I am going to write the balancing equation. mg plus tension T is equal to mv square by L plus k small q capital Q by L square. Capital Q small q by L square. Now I am using the condition tension at topmost point 0. This tension is 0 at the topmost point when we are given with minimum velocity at the bottom. If tension is 0, then I have mg is equal to mv square by L plus k q by L square. Okay, till now everything is clear, right? Now we are moving ahead. So we are using conservation of energy. Actually, we don't use the conservation of energy. We use the work energy theorem because multiple forces are acting and those some of the forces are non-conservative. So we are supposed to use the work energy theorem. But the work done by electric force, centrifugal force and the tension force are zero because forces are acting perpendicular to the displacement. I will show you here. As you look at here, I am taking the vertical circle. Okay, I am taking any random point here. Let's say the particle is somewhere here. Okay, if the particle is here, its weight is acting downwards. That means weight is doing certain amount of work because there is a displacement which is in the direction or against the direction. There is a displacement, and this weight and displacement may be in same direction, may be in opposite direction. That depends on the reference point that we consider. But when it comes to electric force, let's say Fe. Fe is in this direction, whereas the displacement is in this direction. Displacement is in this direction, Fe is in this direction. The angle between the two is 90 degrees. Angle between the two is 90 degrees. Okay. So work done by electric force is 0. Okay, right. Now coming to another force, that is centrifugal force. Let's say centrifugal force is also acting away from the center. Centrifugal force is also acting away from the center. Okay, away from the center. Okay, sorry. Centrifugal force is acting away from the center. Okay, and the displacement is in this direction. Now again, the angle between the centrifugal force and the displacement is again 90 degrees. So the work done by centrifugal force is also 0. Work done by centrifugal force 0. Now coming to another force which acts exactly perpendicular to displacement. If you consider the tension is along the string and the displacement is in this direction, so that angle between tension and the displacement again 90 degrees. So the work done by tension is also 0. Work done by these forces is 0. That is the reason I am directly using conservation of energy instead of work energy theorem. Instead of following the entire analysis, I am directly using a conservation of energy. Okay, I am going to erase all these things. Right. So So mg is equal to mv square by L plus k q by L square. As I have already mentioned, I am not using the work energy theorem, rather I am using the conservation of energy. Okay, from conservation of energy. To apply this conservation of energy, I will follow certain steps. To make you understand better, I am going to follow the step-by-step process because it will help you to solve conservation of energy problems as well. Okay. To use this conservation of energy, first step is to define the reference line. So you can take the reference line. You can consider the reference line anywhere. You can define the reference line anywhere. But I am going to define the reference line here. I am going to draw the diagram again. Okay, so this is the vertical circle that I am talking about, and the particle can be here or can be here, can be somewhere along the circular path. Okay, reference line I am drawing here. So this is the reference line. Now, so this is the center, which is a fixed point. here we have small q and here we have capital Q. Okay, right. Now reference line is here and this length is smaller. This length is smaller. Now first step is define the reference line, which is already done. Now coming to the second step, identify the two states about which you are going to apply the conservation of energy. So as I am talking mostly about bottom and topmost points, I am considering the bottom point as state 1, bottom point as state 1, bottom point as state 1 and topmost point as state 2. Initial, final, state 1, state 2, state A, state B, state bottom, state top, as you are comfortable with. Okay, whatever you are comfortable with. So I am taking state 1 and state 2. Okay. Now the third step is to find the total energy of the particle in state 1 and total energy of the particle in state 2. Okay. First, let's find the total energy. Total energy state 1 is equal to, total energy is nothing but the sum of potential energy and kinetic energy. So potential energy, here we have potential energy 1 plus kinetic energy 1. Potential energy of the particle at state 1, kinetic energy of the particle at state 1. Okay. Potential energy, here we have only gravitational potential energy, because the work done by the electric force is 0, we have left with only gravitational potential energy. As we all know, the gravitational potential energy formula is mgh, where h is height of the particle from the reference line. Okay. So as we are at the bottom, state 1, the height of the particle from the reference line is 0, as this particle is exactly on the reference line. The height of the particle from the reference line is 0. As the height is 0, the gravitational potential energy is also 0. Hope this point is clear, right? Okay. Now let's move on to the next one, that is kinetic energy. As it has certain amount of velocity u at the bottom and the particle has mass m, so the kinetic energy is half m u square, half m u square. So this is the total energy at state 1. Okay. Now let's find total energy at state 2, at the topmost point. Similar process that I am going to follow. Potential energy at topmost point plus kinetic energy at topmost point. Potential energy at topmost point is mgh. H is nothing but height of the particle or point from the reference line. Reference line is here, height of the particle is here. So particle is here, height of the particle is length L and again length L. So the height of the particle will be 2 times length. Now kinetic energy, as the particle has velocity v at the topmost point, the kinetic energy is half mv square, Hope this, total energy at point 2. Now from conservation of energy, total energy at point 1 must be equal to total energy at point 2. Total energy at point 1 must be equal to total energy at point 2. Now what I am going to do is, the terms that I have calculated, I am going to use here. Total energy at point 1 is half mu square. Half mu square is equal to total energy at point 2 is 2 mgl plus half mv square. If I multiply this equation with 2, what am I getting? mu square is equal to 4 mgl plus mv square. I am rewriting this equation for mv square. Yes. So I am rewriting this equation for mv square. Okay. mv square is equal to mu square minus 4 mgl minus 4 mgl. Okay, now I have mv square here, I have obtained the mv square expression here. I can substitute this entire mu square minus 4 mgl in here. Okay, so mv square can be replaced here. Now what am I getting? mg okay, is equal to mv square is nothing but mu square minus 4 mgl, mu square minus 4 mgl by L, as we have L here. Okay, plus kq by L square plus kq by L square, kq by L square. Now what I am going to do is I am going to rearrange this equation again. So I need the minimum velocity. The question is, what is the minimum velocity? That means I have to find the expression for u. So I am going to keep this mu square one side. I am taking the rest of the quantities on the other side. Okay, right. So what I am going to do is I am going to take this term this side. Okay, mu square by mu square by L minus 4 mgl by L. I have divided these terms and I have taken this mg and I have kept as it is, and I have taken this term this side, k q by L. This will be minus kq by L square. Okay, now what I am going to do is I am going to cancel these L's. As we have L here, cancel it. L can be multiplied here, one L will be cancelled here. Okay, now if I clearly write, m can be divide this equation with m, so m get cancelled, m will come here. Okay, now I have got the equation for u square. I have got the equation for u square. U square is equal to this 4gl can be taken to that side, 4gl plus 4gl plus 4gl plus gl, 5gl and another term that we left with is kq by ml, kq by m into L. So final equation that I have got is, come over here. So if I use the square root, u is equal to 5gl, minus kq by Lm under root. Okay, as I have already told you in the very beginning, if you remember the vertical circular motion, at the bottom of the circle the minimum velocity u is equal to root 5 gr. So instead of using r, I am going to use L. Okay, because I have taken L in our case, so 5gl. We have got the similar expression here at the bottom of the vertical circle. Minimum velocity given is 5gl, but there is another force because of the external additional force of electric force between the two charges. We have got additional term here, that is kqq by ml. So this is the expression for the minimum velocity which is given to the particle at the bottom, such that the particle makes vertical circular motion. As I have already told you, the key point is, when you have given minimum velocity to the particle at the bottom, it reaches to the top with certain velocity, but by the time it reaches to the topmost point, the string just about to slack. That means the tension in the string nearly reaches to 0. nearly reaches to 0. Though that is the condition that we have taken. So for minimum velocity at the bottom, the tension at the topmost point, I mean tension in the string when the particle is at the topmost point is 0, and we have used the Newton's second law, that is Newton's laws of motion, balancing the force equation, and also the conservation of energy. Obviously we supposed to use the work energy theorem, but as the work done by non-conservative forces such as tension, centrifugal force, and tension and centrifugal forces is 0, and work done by electrostatic force is also 0, even though it is a conservative force. I have used the conservation of energy directly. Okay, so while using the conservation of energy, I have identified the reference line first, and then I have identified the two states in between between which the conservation of energy is to be applied, bottom and top, and then I have found the expression for the total energy at the 2 points and equated them and simplified them to get the final result, which we have obtained as U is equal to root 5 GL minus KQQ by LM. So this is the final expression, that is the minimum velocity. Okay, hope you have understood the entire explanation that I have followed. If you still unable to follow, please watch it again. If you are facing difficulty in understanding it, please comment below. If you find the video is helpful, please do like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. That's it in this video. Thank you for watching. See you in the next video.